I'd like to thank everyone attending here today, whether you're listening in virtually or in this room with me right now. Once again, I'm Rohit Bose. I'm a senior software engineer at Swim Inc. My social media and email should be available on the slide right now if you have questions that you'd like to ask me offline. Today I'll be discussing how to build streaming data applications with what we like to call properly streaming architectures. We'll come to see that this is no small undertaking in general, but it is something that we found is necessary in order to satisfy the evolving needs of modern streaming applications. I hope that you all leave today with understanding the benefits of streaming architectures and thinking about how they might best fit into your systems. If you could deduce from that, Swim as a company is highly focused on streaming data applications from an end-to-end perspective. And we'll go into the code a little bit as well, but for the most part, this will be a high-level discussion of the benefits of streaming architectures, along with a demo of an end-to-end streaming application. So for a slightly more thorough agenda today, we'll start by discussing streaming data applications at a high level. This will start with some definitions, such as, for example, what they consist of, or the nature of the challenges that they seek to overcome. The next thing I'll try to do is showcase an app that was built with a truly streaming architecture in mind. And what I mean by that is every single piece, from the source data firehose, which is in fact a Kafka stream, to the intermediary computations that are produced by the app, all the way to the real-time UI that's ultimately displayed, will operate on data streams. Every single aspect of that is a data stream. There is a framework that we'll use extensively throughout the demo application. It's the Swim platform, really. I'll discuss the design motivation behind the framework, and I'll show a few code snippets that'll use it. But this won't be a very deep technical dive. But it's I think it's a good level for a general audience. If you do want to see, or if you do want to ask me more technical questions, I'd be happy to do that after the presentation. For timing purposes, I do ask that we save all questions for the end. I'll hold a Q&A session for the last few minutes of this call, and I'll stick around afterward, somewhere in the back of the room, if you want to follow up with me about anything. Okay, so as I promised, I'm going to introduce some definitions of components of streaming data applications here. So the general definition of streaming data is a super broad thing, and I'd like to narrow it down for the specific use case that I have in mind. And I'm going to do so based on some highly recommended properties. First and foremost, here at Swim, we claim that streaming data apps must perform customizable, entity-specific logic with minimal latency. And one common pattern in the industry today is to do that with a microservice architecture. But we at Swim think that's a little restrictive. We still like the term microservices to describe independently developable entities that can be parallelized at runtime, and for the most part, don't care about the exact deployment of its neighbors or things that are running in parallel. So we're going to use this term microservices throughout this presentation, but keep in mind that it's going to be slightly different from a traditional microservice architecture. The next thing we're going to require is that all communication needs to happen through streaming APIs. Now, what we mean by that is there should be almost no situation where a component of the application is wasting cycles, requesting a change or waiting for a change to have happened. Instead, the design of the code should look something like reactions to changes, really, like an event-driven pattern, rather than a fetch and then respond pattern. The third thing we'll insist is that any UIs or any downstream services that require data from intermediary or prior upstream things will be designed with real time in nature. The reason behind all of these is we find that any additional overheads in implementing such an architecture at, say, like the transport layer are well worth the benefits in both performance in the long run and ease of development for any developers trying to build applications. Okay, now what I have here is 3 different properties that we've found that modern apps will demand from you, especially in a data streaming context. So the first definition I have here is this concept of continuousness, where, like, as alluded to in the previous slide, we want a concept of streaming with minimal possible latency. And this is, of course, to meet the demands of like modern applications, because everything is very time sensitive these days. The next definition is this concept of autonomy, which is that, like, in an architecture of stateful microservices, the actionability of any part must be unaffected by the requirements of higher level algorithms. So one other way to phrase that is that every component of the application should be able to act without worrying about what downstream things might rely on. The last thing is observability, which is that for a given set of states, like every single like aspect of those states should be completely inspectable, and there needs to be little to no coordination in terms of actually accessing those states. And for those familiar with like the CAP theorem, you may think that for these properties, it's like they may be like mutually exclusive, such as with, you know, like consistency, like atomicity, and like partition tolerance, consistency, availability, and partition tolerance. You may think that they're mutually exclusive, but we'll insist that these things are not only mutually exclusive, but if you try to take a shortcut and loosen these properties, you're going to be conflicting with the needs of modern streaming applications. It is quite a big ask. So here at Swim, it took us a while to come up with the solution that like meets all this. And that solution is what we've called like the web agent architecture. So yeah, web agent is like just the terminology that we use to describe our general purpose distributed object model of stateful microservices for building end-to-end streaming applications. Now, as the name suggests, the elements of this model were designed to be first-class citizens of the World Wide Web, which may seem at odds with the fact that everything needs to require like streaming, like all network communication should be with streaming APIs. But the World Wide Web was never really like restricted to REST calls everywhere. That's just kind of how the web decided to develop, but it was never a hard requirement of the web. So we'll see, like especially throughout the demo, that when you have like streaming architectures, you can still be a first-class citizen of the web, and it's seamless from an end user perspective. And then in this model, of course, we insist that all UIs and downstream actionable actors are going to be like streaming based. So we'll take that a step in the web agent model specifically. We take that a step further and have designed like this UI engine that's been designed fully with streaming in mind. I am briefly going to talk about web agents like in terms of the model that we have. So for those familiar with object-oriented programming, these analogies will follow very seamlessly. It's like a very one-to-one kind of, just apply what you know about object-oriented programming, and you'll naturally understand web agents. So the idea is that we have these objects, which are the web agents, and they can be distributed over multiple processes, and they're observable. From a code development perspective, they're composable, and very importantly, they're stateful. And like consistent with the stateful microservices that we were mentioning earlier, these objects really are the stateful microservices. Now, in object-oriented patterns, we have web agents, like we have objects that have fields within them, or members. And that's what we're going to call lanes in this web agent model. So lanes are just another word for fields, but they are fully within our web agent paradigm. A nice property of lanes, in addition to like their constant observability, is that they can have actionable lifecycle callbacks. And you'll see that pattern with the links as well, which are like references in an object-oriented analogy. With these primitives in mind, a programmer is able to express apps as logical objects and reactions to changes to those objects. We're very, very different from a traditional REST architecture. And for those familiar with like UI programming or event-driven programming in general, this will be like a natural pattern for you. So in the previous slide, I exclusively showcased or described web agents in terms of object-oriented programming. But for those with other backgrounds, like there are analogies that follow for you as well. My personal favorite would probably be the database one. It follows quite naturally from that, but imagine that instead of executing a SQL query and you get a row back, and that's it, right? That's kind of how SQL works. But imagine if you could get constant streaming updates to that row, and of course all of the columns you get back, like whenever those things incur changes. That's, from a programming standpoint, that's kind of what you see here. But it's a little bit more stateful than that as well. So yeah, even though like from a programming perspective, object-oriented is the best way to follow it, I think the database, if you can think of it like a continuously streaming query, that's another way to like watch our programming model. But I mean, the other things I have up on this slide may help somebody else here as well. Okay. So I've talked a lot about just the general motivation and like the high-level architecture of the web agent model. But I'd like to start getting into the demo because I anticipate that will take most of our time here today. So our demo application spec is actually based on a real-world use case that we have in deployment right now for a customer. This customer is in the telecommunications space, and they have a business need to track the health of a lot of cell towers distributed throughout the nation. So these towers are the things that provide cell service, for example, while like for the cell subscribers and stuff. And the idea is they want to know as quickly as possible if something is going awry with their systems. So maybe the cell tower reported an error type event, and that was published like to some firehose feed that we subscribe to. There's just one possibility. Another possibility could be that the cell tower itself stopped reporting events for a long time. So things that could generally go wrong in a full-scale deployment of cell towers. Now the key thing is like this thing is massive in scale. So for the purposes of this demo application, there are 70,000 of them, give or take a few, spread throughout the nation. But the idea is that each of these towers is continuously reporting. Well, in a healthy state, it would be continuously reporting its own state. And the business use case for that is to identify which towers go awry, like as quickly as possible, and report them in a way that's useful to some end user that's responsible for observing all of this. Because customers are at risk, this is a time-critical need. The error identification needs to be present as soon as possible. And just to be consistent with the needs that SWIM has determined to be mandatory for streaming applications, we're going to like a real-time visualization here. Additionally, we're going to demand that actions can be taken like autonomously. And as a bonus requirement from this particular customer, they wanted some notion of like internal metrics, like from the SWIM platform itself. So we had to go ahead and report that. Now this will be interesting for me as I've never quite done a presentation like this before. But what I'm going to try to do is showcase the demo and have the slides available all at once. So please stand by for a second. All right. I have to paste a URL here. So this is the high-level view of the application. It doesn't look like a lot is going on right now, but you'll find that as I zoom in, a lot of things will pop up, and those things will be rather informative. So right now, what you're looking at is the state of the cell towers throughout the nation, but aggregated by state. And what we mean by that is, like, most of the things are healthy, so we have the map showing like a kind of green, healthy color overall, except it seems that there's some suspicious activity going on in Kansas. So in this map visualization in particular, well, let's make sure Kansas stays red. Maybe not. Well, Illinois is healthy, but I'm going to go with North Dakota because that just turned red more recently. So as I zoom into this map, we'll see that a lot of cell towers have now popped up on here. And you've probably been observing like these ripple effects happening. Each ripple indicates that a new event has been observed like at that time. So in this view, you can more likely see like the full scale of this application, where right now I'm just showing North Dakota alone. And even then, like there's quite a few cell towers like being reported. And this is all real data. At some point, I'll show the WebSocket frames for the more technically inclined, so you can like believe me. And by real data, I mean like it's simulated because we don't have the permissions to actually show the real data. But it's real in the sense that the sense of scale we're getting is similar to what you would see in a production environment. So this particular tower is a different color than the predominant one here. So I'm going to pull it up. And you'll see that this target power of 23250 has like these history graphs and some level of like some metrics that are updating fairly frequently, but at this level of scale, not as frequently as something that would be more exciting. However, like the real sense of scale is that every single tower here is receiving updates right now. So what I can do briefly is refresh this, pull up these WebSocket frames, and now you're just going to see like this huge fire hose of events coming in. They're just going to fly by like faster than you can read them. But that's like kind of one of the things about Swim, where even though you're seeing all these events right now, this downstream client of the web UI is only subscribing to the ones that are relevant to the current view. I've zoomed in on this weird area that includes Minnesota and maybe parts of Wisconsin. And the only events you'll be seeing are either the ones that are relevant to the nationwide level, or the towers in the current view, or the states of Minnesota and Wisconsin. Whereas if I were to zoom out to the point where like we're no longer looking into the tower level view, I'm only seeing data that corresponds to the state level things. So now what I would like to try to do is pull up the slides alongside this demo. How do I close this? OK, well, no bother. I'll just hide that with the slides. And there must be like a slide-only view up here somewhere. Maybe not. Yeah, I see. Okay, so it's like a little bit, the screen's a little bit cut off, so I don't have access to the view menu, but we'll do our best. Is this legible? Oh, there we go. That can work. Now, the main thing I want to highlight here is that this app was built with web agents, of course. So we do have like this Kafka connector that's like demonstrating a fire hose of events that's being sent directly to these web agents. But the key thing that really makes programming a lot easier with the Swim platform is that every single cell tower is treated as its own little microservice / web agent. And we have that same number of 70K of them distributed across, I think in this particular use case, it's only 2 machines. In a production environment, we'd be dealing with even more cell towers or even like more entities in general. And thus it would be distributed across a larger cluster. But this, of course, like the cluster helps us maintain this availability, high availability in case that an event goes down in case a machine goes down, because we do have capabilities in Swim for some machines to be like backups for others in the case of failure. But yeah, the takeaway here is that we have all these tower agents like concurrently running in real time, all 70K of them, and on some cluster of N machines. In this particular case, N is 2, and it's hosted on Swim Cloud. In addition to like these tower type web agents, we have this concept of a state web agent, which is much lower in scale at, of course, only 50 of them per state. And these represent like aggregate data. So they not only will track their own little things that are relevant to them, such as like their bounding boxes, which are helpful for drawing this map, but they will also track like the states of all the towers that are lying underneath them. So of course, like something like California will have a ton of tower type web agents that this state will subscribe to. And you can see it like blowing up this web UI here. On the other hand, something like Rhode Island. Where is Rhode Island? My geography teacher would not be pleased. But okay, I found Delaware. Let's go with Delaware. Providence is Rhode Island. Right below. Oh, thank you so much. Yeah, so Rhode Island, on the other hand, is, you can still see a large stream of events here because each of these is receiving a lot of data, but it's much smaller scale as opposed to like California. So yeah, if you really like think of the scale of events that are going on here, and this is just for like a demo application, like it's quite insane. And again, for the technically inclined, you'll notice that we've only opened one WebSocket connection here. Even though we're running this on a cluster of machines, like we have multiplexing / demultiplexing built into the Swim platform. So even we have all of these uniquely addressable things over one physical connection. And that's like a huge benefit for us because as a programmer, you only care about the objects and how they're distributed in space. You don't care about like looking up where you need to go, apart from, of course, you need one like single centralized like reference point to do that. But once you have that, like you have full access to everything that's relevant to that like nicely composed runtime. I did have the slides here that I do want to go back to. I'll have to zoom out. So yeah, just to recap what I was describing earlier about the tower agents, they're retrieving network metrics that represent their own health from the Kafka firehose, really. And they're just going to statefully model the current state of this tower, but they're also doing some sort of computations. Let's see. Yeah, of course. Like at the top of these KPIs, you'll see that we're actually doing some math here because every event that this receives only represents like a single event. The events themselves don't have any computations in them. The Swim platform has to be doing that kind of stuff. And if I have time towards the end, I'll be able to show you what the code for that looks like. And yeah, just a brief slide about the state agent as well, which is doing exactly what the tower agent is doing at the state level, but it's also receiving the real-time state of every tower that's like underneath that. So yeah, it's effectively the same thing, but it's aggregating all of the data into one like centralized kind of thing. Okay. There is one other view that I haven't really shown, and I will do that shortly. But this handles the metrics requirement that the customer had for us previously, where they not only wanted to see the data that was relevant to them, but they wanted to inspect the internal metrics that Swim was undergoing. So if I go back to, right, one day I'll figure out how to close this. Maybe I'll just use the keyboard shortcut. Oh, there we go. There's another view here that is actually cut off by the display. Okay. So this is kind of like the meta view. And I hope it's not cut off for you guys in the display. And it's just the screen here. But the idea is this is a general purpose thing that can be served up by any Swim application, really. Because we're treating web agents as these like distributed objects that don't have very strict types, but have these general patterns. And as a result of that, we can do some general purpose UIs that can track the health of the agents. So for example, if you wanted to dive down to a state, these are like URI prefixes. So under the state of United States, if we wanted to look at the state of California, because why not? These are the different lanes that are being populated in real time. And you'll see that this particular alerts lane is used to represent like alerts served up by cell towers that belong to the state of California. And again, completely real-time updates. The protocol that we use is served up over WebSockets, so there's no like fetching involved. It's really like ask and receive all the stateful updates. This is a static thing, so even though we're operating strictly on streams, you can serve static data from those streams. You'll see that this never changes, but it's the bounding box required to draw the state of California on a map. Info is not very, info is not very exciting. That's all it has, really. Status updates very frequently because it's a summary statistic that's based on a lot of different aggregations. Subregions we don't really have at this level. And then sites updates insanely frequently because it's not only representing like the current, like all the sites in the state of California, but every time it changes this severity summary statistic, it'll draw a new entry onto here. And I know that I'm running out of time here, but one thing that would be neat to show is like the Swim CLI. In order to show like we have one physical network stream, but the idea is that you can subscribe to arbitrary subsets of that stream at any time. And that's really what the UI is doing. You'll notice the UI linking and unlinking to certain streams depending on the current view. That's probably way too small for you guys. So right now I've just shown you some demo commands. If you wanted to run this locally, that's what I would use. But for the sake of time, I chose to use the cloud version. So yeah, let's just run. I can't use that host. So I'll just type it out since that will probably be easier. So if I do swim CLI sync, I type in the host that we're going to use. Warp S is like secure. cellular1.swim.services. And then I'll use the node that's the state of California which has a URI pattern that uses like this. So what I've typed here so far uniquely identifies a web agent. And the next thing I'll type out with the lane flag uniquely identifies a lane within that web agent. So this command that I'm about to run will be identical to to what I showed you in the UI previously. Yeah, you'll see that exact same stream coming in, but this time through a CLI instead of the web UI. And this just represents me subscribing to one stream within the server that's serving up like thousands, at least 70,000 different streams. But again, like you can define the subset. So if I wanted to do Maryland, I can do that too. And other example streams that you can subscribe to with this pattern are, well, let's rerun the Maryland one actually, because I want to do something. I want to just look at this 5839 site now. So to do that, you'll see that this corresponds to this pattern here. And if I look at the info lane here, see that this thing is not updating very frequently. The key performance indicators might update a bit more frequently. But the idea is that I can subscribe to any number of these streams at once, and my UIs and downstream applications will be built with this flexibility in mind. So we really, really emphasize the need for like streaming APIs here. And any downstream services that utilize them must be aware of streams and how to coordinate them and things like that. Because the benefits you get are like very, very dramatic. Like it would be much harder to build an app that handles this level of scale without this assumption of like streaming data everywhere. Yeah.
Rohit, I love the enthusiasm. It looks great. We are at the end of time.
Okay, yeah, sorry. I saw the 2 minutes on the clock. I assumed but it's okay.
That's okay.
Yeah.
It's okay. We should sort of be in questions now. So if anybody's got any questions, Rohit, I suggest you go to the back and take them back there.
Yeah, I'll stick around at the back of the room for any questions or follow-ups that you might have. Just very briefly, because I know this is being recorded, I'd like to pull up some of the useful links that I have on this last slide. Oops. Yeah. If you want to explore the Swim stuff more, we have like our main landing page, we have our developer site, we have our GitHub, and 2 more demo apps that you can just like view, and they're hosted directly on the Swim cloud. Right. Thank you very much for the time.